Hess's law states that when reactants are converted to products, the change in enthalpy, delta H, will be the same whether the reaction takes place in a single step or in a series of steps. The keywords over here are reaction, in one single steps, or in a series of steps. To represent that graphically, we can look at this diagram over here. Let's say we have a reaction from A to convert into B. So A convert into B, this is the single step reaction, and it has the delta H value, a certain value over here. So you have another pathway of converting A into B, but the second pathway, the one you look over here, this one, A needs to be converted into X, and then from X converts into Y, and then Y, then it will be converted into B. So the one on top, the one that you are looking at here, this is the part in which the reactions are in a single step. So that is the single step, and it has the value of delta HR. And the one that you have at the bottom, the one over here, those are in a series of steps. Okay? So the value, when you add up delta H1, delta H2, delta H3, will be the same as delta HR. So that is what it meant by Hess's law. The change in enthalpy will be the same whether the reaction is going to be taking place in a single step or in a series of steps. Let's have a look at another example. Let's say we have A converts into B. You have delta HR, and then A convert into M, and then M converts into N converts into P, then P converts into B. You will have another reaction, perhaps M directly to B or N directly to B without going through P. Therefore, over here you have delta H1, delta H2, delta H3, delta H4, and then here delta H5, delta H6. So the one that you are looking at right there, that is in the single step. Okay, and the value of delta HR over here, it will be the same if you're going to take the roots over here, the one in purple. If you add up H1, delta H2, delta H3, delta H4, the value will be the same as delta HR. Same goes if you want to take this roots over here. When you convert from A into M, the value of delta H1, when you add up with delta H5, it will be the same as delta HR as long as you're going to end up the same products as the single step reaction. Same goes to if you want to take the other roots right there. When you have delta H1 plus delta H2, delta H6, and you convert directly to B without going through P, the adding up of delta H1, 2, and 6 will be the same as delta HR. The enthalpy changes can be calculated by using two methods. We're going to look at the algebraic method, and second, we're going to look at the energy cycle method. Hey guys, in this video, we're going to look at how we're going to use the energy cycle methods to solve problems related to Hess's law. Before you're going to do that, I would highly suggest you to watch the algebraic method first, because the energy cycle method is related to all the steps in algebraic method. The link will be on top. So when you have a question like this and you are required to solve this by using the energy cycle method, what you need to do now, you have to do step number 1, which is do the necessary alterations by doing reversing or multiplying, just like what we have done in the algebraic method. So when you do the alterations, you'll do something like this. You're going to look at the target's equation. You're going to give the number for your first, second, and third thermochemical equations. You'll do the multiplications and the reversing based on your target's equation, and then you'll get something like this. Okay, you're going to have your target's equation, you have your altered thermochemical equations, and this one is just your reference. We haven't done the energy cycle method yet. Okay, for the algebraic method, you will be canceling out things. But for the energy cycle method, it is compulsory for you to solve this by constructing the energy cycle. And how are we going to do that? Okay, so we're going to take the target's equation on top. You're going to write it on top right over here. And take that, the first one, 2 carbon solid. And look for 2 carbon solids in the thermochemical equation, of which you have altered. And we have found that the 2, I'm going to use purple. Okay, so 2 carbon solid is right over here. It's on equation number 1 that is multiplied by 2. So I'm going to take this whole thing. Okay, I'm going to take that whole thing. I'm going to take this arrow and push that downward to make 2 CO2 gas. Exactly like what I'm going to do here. So I'm going to take that going down there. Okay, to make 2 CO2. So you'll have 2 CO2. And on the arrow here on top, I'll take 2 O2 gas. Okay, I'll write 2 O2 gas. 2 O2 gas on top of that arrow. So we're done with this bit. And what about 2 CO2? Okay, so we're done with that one. For 2 CO2, when you look at there, can you find 2 CO2 in the other thermochemical equation? And the answer is yes, you can find it right. I'm going to use black right here. Okay, so you can take that and you combine this and you continue with whatever you have here. Okay, obviously from 2 CO2, you will be making C2H6, which is the end product of the target's equation. So 2 CO2 producing, reacting with water, you're going to make C2H6 right here. So we're going to write plus 3H2O gas. Okay, you have 3H2O gas making C2H6 gas. Okay, so you get C2H6. You're just going to take the arrow like that and Do you need to write anything on the arrow? Yes, as you can see right there, I'm going to use red. You have 7/2 oxygen gas will be producing as well. For that, you don't have to write it over here. You can write it on top of the arrow. Okay, so you have 7/2 O2 gas. Okay, will be part of the thing. And to make it completed, look at this bit. That one needs to be connected as well. So when you look at this thermochemical equation, the only thermochemical equation we haven't done yet is the purple bits. When you look at the purple bits, this is 3H2 gas, and we'll be making H2O, which is that part of that H2O. So we take 3H2 gas and making H2O, 3H2O. You're just going to be taking this, take that arrow like that, and on top of that arrow, on the side of that arrow, you're just gonna write 3/2 oxygen gas, the one that you have over here. Okay. So you get 3/2 oxygen gas. So this is how you're going to construct the energy cycle method. So when you construct this energy cycle method correctly, you'll get 1 mark for this, 1 mark for that bit, 1 mark for that bit, and 1 mark for here. On top there, you need to find that. And then finally, you're just going to be adding up all the value that you have to get the delta HF. So this bit, you get 1 mark, and HF, you get another 1 mark. And these are just the values that you have constructed over here. That's why it's very important for you to do the first step first. Do the necessary alteration, reversing, multiplying, just like in algebraic method, and you altered what you have over here. You get this, and from whatever you have in there, you transfer it into energy cycle method, and you're done with it. Let's have a look at another one. So this is also another examples of you can use algebraic method to solve this, but if the question wants you to use energy cycle method, you have to do the same thing. First, do the alteration based on what we have talked about in the algebraic method, and you get something like this. You identify the target's equation. You numbered all the thermochemical equations given. Do the multiplication and reversing based on the target's equation. And you have the altered version of the list of thermochemical equation. From here, you're going to use this as a to check your answers afterwards, if it's correct or not. Okay, so because this one is not algebraic method, you don't have to show the canceling process. Okay, but what you need to do is you need to construct the energy cycle. We're going to do the same thing. So first, you're going to write the target's equation on top like this. Okay. And we're going to start with the one in front, 2 carbon solid. So 2 carbon solid, I'm going to use purple. 2 carbon solid, where can you find it? You can find it in the first equation, 2 carbon solids over there. And when you look here, you have 2 carbon solid, will be producing 2CH. It should be 2CF4 gas. Okay, 2CF4 gas right there. Okay, so just gonna write that. You're gonna take 1 arrow going down, 2CF4 gas. And on the side of the arrow, you're going to write 4F2 gas, which is that. Okay, now we're going to try to make a connection between 2CF4 gas with C2H4 gas. Let's see if we can do that. We stopped right here, 2CF4 gas. And when you look there, there's 2CF4 gas on the third reversed thermochemical equation. It will react with 4H4 gas, making C2H4 gas, which is the product of the target's equation. Okay, so we're going to write plus 4HF gas to make C2H4. And on the side of the arrow, you will have 6F2 gas. Okay, you have 6F2 gas. And then you've done that. And then when you look at 2H2, you have 2H2 right there in yellow. That is right there, 2H2. And it will be making 4HF gas. And on top of the arrow, you have 2F2 gas. So we take this, you take that arrow going down there. And on top of the arrow, you have 2F2 gas. On the side of it, you have 2F2 gas. Okay, so by constructing the complete diagram, here you get 1 mark. The one going that direction, 1 mark. Going down direction, 1 mark. And don't forget to write the delta HF right there. And finally, what you need to do is you just need to write the exact same calculation as what we have done for algebraic method. You're going to add up all of them. So you get 1 mark over here, and you'll get 1 mark for that. That is how you're going to do the algebraic method and also the energy cycle method. Remember, before you want to understand what's going on in the energy cycle method, it's better for you to watch the algebraic method first. It's very important for you to get the target's equation and the altered thermochemical equations right over here before you want to construct your energy cycle.